Hello, everyone. In this section, we will introduce the characteristics of a p-n junction without bias in electronics. In the previous section, we introduced that a neutral intrinsic silicon semiconductor becomes a neutral p-type semiconductor after being doped with neutral group 3 elements. The concentration of the acceptor dopant is Na. At room temperature, the acceptors can be fully ionized and generate holes. Since each group 3 dopant atom creates one hole, the hole concentration in the p-type semiconductor, pp0, is approximately equal to the doping concentration Na. After the holes are generated, the p-type semiconductor can be regarded as containing negative space charge, Na-. Notice that the amount of negative space charge is balanced by the positive charge of the holes, so the p-type semiconductor is still neutral overall. The minority carrier electron concentration, Np0, is Ni squared divided by pp0, so its concentration is quite low. Therefore, we can simplify the diagram of a neutral p-type semiconductor as shown on the far right of the slide. It is a p-type semiconductor composed of negative space charge and positively charged holes. Similarly, a neutral intrinsic silicon semiconductor becomes a neutral n-type semiconductor after being doped with neutral group 5 elements. The concentration of the donor dopant is Nd. At room temperature, the donors can be fully ionized and release electrons. Since each group 5 dopant atom releases one electron, the electron concentration in the n-type semiconductor, Nn0, is approximately equal to the doping concentration, Nd. After the electrons are released, the n-type semiconductor can be regarded as containing positive space charge, Nd+. Notice that the amount of positive space charge is balanced by the negative charge of the electrons, so the n-type semiconductor is still neutral overall. The minority carrier hole concentration, Pn0, is Ni squared divided by Nn0, so its concentration is quite low. Therefore, we can simplify the diagram of a neutral n-type semiconductor as shown on the lower right of the slide. It is an n-type semiconductor composed of positive space charge and negatively charged electrons. When a p-type semiconductor and an n-type semiconductor are connected together, a p-n junction is formed, as shown in the figure. The p-type semiconductor has a high concentration of holes and a low concentration of electrons. The n-type semiconductor has a high concentration of electrons and a low concentration of holes. Therefore, once the p-n junction is formed, one of the carrier transport mechanisms mentioned in the previous section, diffusion, will occur. When holes diffuse to the right and electrons diffuse to the left, many electrons meet many holes, and recombination occurs. In recombination, electrons in the conduction band transition back to the valence band to fill the empty states, which are the holes. Therefore, after electrons and holes recombine, the electrons in the conduction band and the holes in the valence band vanish, as shown in the figure. After hole diffusion and electron diffusion lead to recombination, the originally neutral p-type and n-type regions lose holes and electrons near the junction. As a result, a net space charge appears. On the p-type side, the space charge density is Na-. On the n-type side, the space charge density is Nd+. According to Gauss's law, the gradient of E equals rho divided by epsilon. Here, rho is the volume charge density, and epsilon is the dielectric permittivity of the material. Gauss's law tells us that when net charge exists in space, a gradient of the electric field E is produced. In other words, an electric field appears. The electric field points from positive charge to negative charge. The electric field direction is the force direction for positive charge, such as holes, and the opposite of the force direction for negative charge, such as electrons. From the figure on the right, we can see that holes in the neutral region of the p-type semiconductor are driven to the right by diffusion. However, the electric field produced by the space charge exerts a force on the holes toward the left. These two forces are in opposite directions. Similarly, for electrons in the neutral region of the n-type semiconductor, diffusion drives them to the left, while the electric field produced by the space charge exerts a force toward the right. These two forces are also opposite. When the amount of space charge is small, the electric field is weak, so the electric field force is much smaller than the diffusion force. Therefore, holes in the p-type region and electrons in the n-type region continue to diffuse and recombine, creating more space charge. This makes the space charge region wider, which strengthens the electric field and increases the force that prevents further diffusion of electrons and holes. Eventually, the diffusion force and the electric field force on electrons and holes reach equilibrium, and diffusion stops. The width of the space charge region in the p-type semiconductor is xp, and the width of the space charge region in the n-type semiconductor is xn. Because there are no mobile electrons or holes in the whole space charge region, this region is also called the depletion region. Because the whole semiconductor is electrically neutral, the number of vanished holes equals the number of vanished electrons. The vanished holes create negative space charge in the p-type semiconductor, while the vanished electrons create positive space charge in the n-type semiconductor. Therefore, according to charge neutrality, the total negative space charge in the p-type semiconductor equals the junction area A multiplied by xp, which gives the volume of the space charge region, then multiplied by the charge density Na and the charge amount Q. This equals the total positive space charge in the n-type semiconductor, which is the junction area A multiplied by Xn, then multiplied by the charge density Nd and the charge quantity Q. In summary, as shown in the figure on the right, the space charge produced by diffusion induces an electric field that resists the diffusion force. When the electric field force and the diffusion force reach equilibrium, a built-in electric field has already been formed inside the p-n junction. By integrating this built-in electric field with respect to position, we can obtain the built-in potential difference, V0, from the neutral p-type region to the neutral n-type region, as shown in the figure. This potential difference forms an energy barrier, which prevents holes and electrons from continuing to diffuse. Therefore, once a p-n junction is formed, an electric field and a potential difference already exist inside the structure, even without any external voltage. In general, this built-in potential difference, also called the built-in voltage V0, is approximately between 0.6 volts and 0.8 volts. The width of the space charge region, also called the depletion width, W, is equal to xp plus xn. As shown in the equation on the slide, W equals the square root of 2 epsilon s divided by Q, multiplied by 1 over Na plus 1 over Nd, multiplied by V0. According to the charge neutrality relation, we can obtain the depletion width on each side. For the p-type semiconductor, xp equals the total depletion width W multiplied by Nd over Na plus Nd. It can also be written as the square root of 2 epsilon divided by Q multiplied by Nd over Na multiplied by 1 over Na plus Nd and multiplied by V0. For the n-type semiconductor, Xn equals the total depletion width W multiplied by Na over Na plus Nd. It can also be written as the square root of 2 epsilon divided by Q multiplied by Na over Nd multiplied by 1 over Na plus Nd and multiplied by V0. From these equations, we can see that when the semiconductor doping concentration is higher, the depletion width becomes narrower. After the space charge widths of the p-type and n-type semiconductors are found, we can calculate their space charges, Qjp and Qjn, as shown in the equations on the slide. Their charge magnitudes are equal because of charge neutrality. Therefore, this charge is called the junction charge, Qj. Finally, let us summarize several important formulas for the p-n junction. First, when the p-n junction is fabricated, the doping concentrations of the p-type and n-type semiconductors, Na and Nd, can be determined by the fabrication process. After Na and Nd are determined, the first key characteristic we can calculate is the built-in voltage, V0. V0 equals kT divided by Q, multiplied by the natural log of Na times Nd divided by Ni squared. After finding V0, we can then calculate the widths of the space charge region, W, Xp, and Xn. Finally, we can calculate the junction charge, Qj. That concludes the introduction to the characteristics of a p-n junction without bias. Please look forward to the next class. See you next time. Bye-bye.